Hello guys, welcome to another calculus video. Today we're going back from physics and we're taking a look at some awesome generalized integrals. And we're looking at these two integrals right here, and we're going to get some great cameos from the Riemann zeta function and the gamma function. And let's get started. So the first integral we're going to look at is the easier one, and that's the integral from 0 to infinity of x to the n over sine hx, hyperbolic sine of x. Now the way we're going to do this is we're going to use a pretty typical trick when you have a hyperbolic function in the bottom because, well, you'll see what it is. So let's just go ahead and plug in the direct definition of sin hx. Now, the cool trick that I like doing when I have sin hx on the bottom is I'll multiply by e to the negative x in the top and bottom. So what's going to happen is we're going to end up with 2 to roll from 0 to infinity, x to the n, e to the negative x on the top. And then the bottom, we're going to end up with 1 minus e to the negative 2x dx. Now what we're going to do is we're going to apply the power series for 1 over 1 minus x, which is equals 0 to infinity of x to the n, right? So we're going to apply the power series to this part on the bottom. So we're going to end up with 2 times the integral from 0 to infinity times x to the n, e to the negative x, times the sum from n equals, or actually I can't use n, I'm going to use k because I need a different letter here, 0 to infinity of e to the negative 2kx, sorry, dx. Then what we're going to do is just take this sum to the outside, so we're going to end up with 2 times the sum from n equals 0 to infinity of the integral from 0 to infinity of x to the n, and then then we're going to add negative 1 and negative 2k, so we're going to end up with 1 plus 2k x negative sine dx. Then we're going to really quick substitute 1 plus 2k x equals u, or x equals u over 2k plus 1. Then dx equals du over 2k plus 1. And so when we substitute that, we're going to end up with 2 times the sum from k equals 0 to infinity. Yeah, sorry, I put an n here. Force of habit. This should be a k. And then we're going to end up with 1 over 2k plus 1, bringing that to the outside. Integral from 0 to infinity of u over 2k plus 1 to the n. So I'm going to go ahead and bring the 2k plus 1 to the outside. So we're going to end up with just, and of course this other part just ends up being e to the negative u du. And so this is gamma of n plus 1. So I'll just replace that. We'll write it as n factorial actually, because that's also what it's equal to. But just know that it can be extended to non-integer numbers just using the definition of the gamma function. Now, this part that we're left with is kind of a nasty sum, but it kind of reminds us of our friend, the zeta function. Now, I'm sorry, I can't draw a zeta for the life of me, so I'll just draw like, I don't even know what that was. So zeta of s equals the sum n equals 0 to infinity of 1 over n plus 1 to the s power. Now I'm going to do a neat little trick here. If I do 2 to the negative s times zeta of s, I'm going to end up with the sum from n equals 0 to infinity of 1 over 2n plus 2 to the s. And so what this is this is kind of summing up the s 1 over every integer to the s power, but this is just summing up the even integers. So if I do this first one minus this second one, we'll just end up summing up only the odd integers, or basically we can say 1 minus 2 to the negative s times zeta of s equals the sum from n equals 0 to infinity of 1 over 2n plus 1 to the s. So we're going to do that same trick. In this case, s is just n plus 1. So this whole thing is going to turn into 2 n factorial times the sum from k, or sorry, not the sum, times 1 minus 2 to the negative n plus 1, right? Times zeta of n plus 1. So if we go ahead and plug in a few examples here, obviously if we plug in 0, it's not really going to work out that great because we're going to have that asymptote at 0. But if we plug in, for example, n equals 1, then we'll end up with 2 times 1, do n equals 1, 2 times 1, and then times 1 minus 2 to the negative 2. So 1 minus 1/4 is just 3/4. And zeta of 2 is just pi squared over 6. And so what we'll end up with is this and this cancel with this, and we end up with pi squared over 4, which is the integral from 0 to infinity of x over sin hx. Similarly, if we plug in n equals 3, we can do 2 times 6 times 1 minus, that's going to be 1 over 16, so 15/16. And then zeta of 4 is known to be pi to the 4th over 90. And once we simplify all those fractions, this equals, I believe, pi to the 4th over 8. So now let's take a look at our other integral. Now the reason I didn't do this other integral first is because I couldn't actually find a good closed form for it, but we can find a few values of it. So we're going to do the exact same thing that we did before, so I'll kind of speed up with the steps here. I'll just mention the things that are different. Now the main thing that's different here is because we have this plus sign, we need to remember to add a -1 to the n when we convert to a sum. So as you can see here, we've ended up with 2 times n factorial times the sum from k equals 0 to infinity of -1 to the k over 2k plus 1 to the n plus 1. And so there's no, as far as I know, there's no good general formula without using some pretty complex functions. Like I plugged this into Wolfram and it gave me something in terms of the generalized Riemann zeta function, which to be honest I've never heard of. So there's no real good closed form for this, but for a few certain numbers that we plug in, we can get a good value. So for example, if we plug in n equals 0, we'll end up with 2 times the sum from k equals 0 to infinity of -1 to the k over 2k plus 1, and this is well known to be pi over 4, so we get 2 times pi over 4 or pi over 2. And for n equals 1, we get the sum from k equals 0 to infinity times 2 -1 to the k over 2k plus 1 to the 2. And this is known to be Catalan's constant, so this just ends up being 2 times c, where c is Catalan's constant. So those are the real only ones that we can really evaluate well. If we put in some higher powers, we can get some numbers that we do recognize, but unfortunately, there's no real general form for all n. So I hope you enjoyed this video and these cool integrals, and I'll see you in the next one.